Hey guys, so today we're going to be covering Chapter 6 of the Environmental and Natural Resource Economics course. And so I'll be working off the Tom Teterberg 9th edition book, and this is a course usually offered across North American colleges and universities in the economics program. Okay, and so in Chapter 6, the topic we'll be covering is the depletable resource allocation strategy, and how do we make decisions based on consumption in this generation and for future generations? Do we consume everything today, or do we save some for tomorrow? Okay. So before we begin, I think it's important to really ask ourselves a few important questions. So how do societies react when finite stocks of depletable resources become scarce? Is it reasonable to expect that self-limiting feedbacks would facilitate the transition to a sustainable steady state? Or is it more reasonable to expect that self-reinforcing feedback mechanisms would cause the system to overshoot the resource base, possibly even precipitating a societal collapse? So this is quite an important question because across history, we've seen many examples of societies facing scarce resources, whether it was food or maybe it was capital stock, and there was a negative, there was a collapse in certain societal mechanisms. I mean, the worst case would be the Incan example, where they faced a food shortage and their harvest season did not create that sustainable flow of food for several years, and eventually they did not save enough and their society went extinct. On the other hand, looking at our developed economy, when we talk about maybe the problem of fossil fuels and our dependence on fossil fuels, well, based on the technology we have today to harness hydropower and solar energy and nuclear energy, well, maybe we can facilitate a steady, sustainable transition to more renewable energy sources. So it really depends upon the situation and the decisions our leaders will make. Now, before we really go into more of the illustrative examples, I think it's important to really define the types of resources and the reserves that we're going to be referring to. So there are three separate concepts that are used to classify the stock of depletable resources: current reserves, potential reserves, and resource endowment. Now, current reserves are known resources that can be profitably extracted at current prices. Potential reserves are the amount of reserves potentially available dependent upon the price people are willing to pay for those resources. Now, the resource endowment represents the natural occurrence of resources in the Earth's crust. It is the upper limit on the availability of terrestrial resources. So let's put these definitions using an example into context. So say, for example, we're talking about oil. Well, if we were to talk about the current reserves of oil, essentially what we'd be referring to is the current millions of barrels of oil equivalent that are being extracted at the moment at the current price level of $50 a barrel of oil. Okay? Potential reserves are essentially the exploration interest, the potential reserves that a lot of oil companies have in their inventory that they own, but are not currently mining or extracting because it's just not profitable. They're waiting for a higher price of oil in order for them to invest and build invest in the necessary equipment in order to extract that oil. So once the price of oil increases, then potential reserves become current reserves because we can then mine those reserves at current prices. Now, the resource endowment is essentially every single drop of oil available on Earth. It is the upper limit. It is all the oil that can be found on the bottom of the ocean, that can be found in the Earth, and it is, again, if we had an infinite price for oil, then it would be profitable because in the end, the companies would find every drop of oil, invest as much as they could, and then they'd extract that oil. But it's really unrealistic to assume that all of this oil that is set as the upper limit of the resource endowment is possibly going to be extracted. It's highly unlikely because there will be a lot of unprofitable shale or basin areas across the world where you'll need maybe $300 or $400 per barrel of oil, which is highly unrealistic at the moment. Now, the distinctions between these three concepts are significant. Two mistakes when we're talking about these three concepts are, first off, using data on current reserves as if they represented the maximum potential reserves, and second, assume that the entire resource endowment can be made available as potential reserves at a price people are willing to pay. So the first mistake essentially underestimates the amount of reserves available. So if we were to assume that our current reserves are also the potential reserves, that would be very short-sighted, because in the end what we're saying is that, oh, because of this price level, this is only the potential reserves that are available to us. Well, no, if the price of oil doubles, then you can go find other basins that you could mine and extract oil from there, and that would be considered your potential reserves from now. So the first mistake really underestimates the amount of potential reserves available. The second mistake overestimates the amount of potential reserves available, and it assumes that every drop of oil available on Earth should be considered as a potential reserve. Well, I mean, hypothetically, that is true, because say, for example, the price of oil was $1,000 a barrel, then yeah, I mean, like that, then you will see a significant portion of potential reserves accessible and available to the company. But it's highly unrealistic, and it's unfair to assume an infinite price to mine the very last drop of oil at the deepest part of the ocean. It just doesn't make sense. Okay? Now, some other terms that are used, I do a lot of research on mining companies and oil companies, and some of these are the terms they use in their research reports. So you have identified reserves, which are probably the highest confidence level. There's maybe a 1% margin of error, and the company is highly confident that there is X amount of barrels of oil equivalent in the ground at this location. Now there's measured resources, maybe there's a 20% margin of error, all the way down to speculative resources, where they don't really know anything about that reserve. All they know is they're speculating. I think there's X amount dependent upon my assumptions, all that. So essentially I've ordered all of these terms based on the confidence level. So the identified reserves would probably be, you would be the most confident that there's X amount of barrels of oil in the ground right here, and speculative resources, you're the least confident. You're probably 99% unsure that there is X amount of oil in the ground here. Okay? Now, from an environmental economics perspective, we'll be referring to resources through three different definitions. So a depletable resource is one for which the natural replenishment feedback loop can be safely ignored. Essentially, the best example is fossil fuels. The feedback loop and the replenishment rate would require millions of years for oil to be created again. In the end, for the crayfish to fall to the bottom of the ocean, and then millions and millions of years of sand to put pressure on those remains to form that oil, it just doesn't make sense. Like, it's going to take too long. So we can confidently say that it's a depletable resource. Now, a recyclable resource is one that, although currently being used, exists in a form allowing its mass to be recovered once that purpose is no longer necessary or desirable. And the best example is paper. You make paper, a company produces paper and then sends it to all the corporations on Wall Street or Bay Street, and then those corporations recycle that paper. Well, that mass is not gone. It's not being unused. Well, it just goes back to a recycling center and then is reused again. So it's a recyclable resource. Now, a renewable resource, its natural replenishment augments the flow of renewable resources at a non-negligible rate. So essentially, solar energy is the best example. As much solar energy as we can use, that will not impact the reserves of that resource. In the end, there will be millions and millions of years of solar energy, and we can assume that is a renewable resource. Okay. For some renewable resources, however, the continuation and volume of their flow depends crucially on humans. Soil erosion and nutrient depletion reduce the flow of food. Excessive fishing reduces the stock of fish, which in turn reduces the rate of natural increase of the fish population. For other renewable resources, such as solar energy, the flow is independent of humans. So we've already talked about solar energy. However, focusing on the first part of this slide, yes, this is true, especially when you're talking about the efficiency of soil. If the nutrients available in that soil decline or somehow they get poisoned, dependent upon our pollution or something, then the flow of food will decline. And so we have to take care of that. Although food is considered a renewable resource, we need to make sure that we're protecting the land, that we're ensuring that nutrients in the ground remain efficient and remain at a sufficient level that our flow of food continues at a steady rate. So there is a risk that for some renewable resources, that steady flow declines over time. Storing depletable resources extends their economic life. Storing renewable resources, on the other hand, can serve as a means of smoothing out the cyclical imbalances of supply and demand. Essentially, a renewable resource, its price will be quite consistent, especially from a marginal cost perspective. But depletable resources, over time, that price, as always, as you use more and more and more, there are less and less and less, the price will increase. So it makes sense that when you're storing depletable resources, it extends their economic life and it adds value to that resource. It adds value to those holdings. Whereas when you're storing a renewable resource, all you're really doing is you're saying, okay, if this is X amount is the flow of food right now, and we're using less than that, then let's store some for a period when we know that we're going to use more than X. And so it's more focused on smoothing out the cyclical imbalances of supply and demand. The challenge for depletable resources involves allocating dwindling stocks among generations. In contrast, the challenge for managing renewable resources involves the maintenance of an efficient, sustainable flow. And so the first part of the sentence, the challenge for depletable resources involves allocating dwindling stocks. That is what we're going to be talking about in this chapter. And so you'll see that in the second case, and actually in both cases, you'll see that the renewable resource offers an out. It offers a way for a society to make a switch from a depletable resource to a renewable resource in order to remain sustainable and remain in that steady state. Now let's look at an example. So we talked about, in chapter 5, we talked about intertemporal allocations in a two-period model. And so the objective was to max the present value net benefit. And so we looked at this and we said that, okay, this is period 1 and this is period 2. And period 1 usually, and the way it worked with the two-period model is that because based on, the present value factor, in the end, our present value net benefits in the earlier period, we wanted them to be higher than in the latter period, because in the end that would maximize our present value of net benefits. However, if we were to extend the horizon and go beyond a 2-year model, a 2-period model, well, then things change. But before we do that, I think this is probably the most important slide in the entire deck, okay? This is really important. Okay, you need to understand the marginal cost of extraction and the marginal user cost. In the two-period model, the marginal cost of extraction is assumed to be constant. And so what marginal cost of extraction means, essentially it's the marginal cost of me going and mining that ore body, or me going and digging deeper for more oil. Essentially, if marginal cost of extraction is assumed to be constant, what that assumption implies is that if I have an ore body that's a kilometer deep, well, if it cost me $1 million to mine the first kilometer, and it will cost me $1 million to mine the next kilometer. So the marginal cost of extraction remains the same. Now, the rate of increase in the current value of the marginal user cost is equal to R, the discount rate. And so we talked about the present value formula and how you want to discount benefits back to the present value. And when you're talking about the marginal user cost, essentially the marginal user cost is if I'm going to consume this resource, this depletable resource, then the marginal cost of me consuming that is the marginal user cost, and it increases at R. Because in the end, the marginal user cost rises at rate R in an efficient allocation in order to preserve the balance between present value versus future production. Okay? Now, why does marginal user cost increase? Due to the fixed and finite supplies of depletable resources, production of a unit today precludes production of that unit tomorrow. Thus, production decisions must take foregone future net benefits into account. This increasing opportunity cost drives marginal user cost when the marginal cost of extraction is constant. Okay, that's complicated. Let's simplify it once again. So essentially why marginal user cost increases is that if we're considering future generations, if we consume today, there is an opportunity cost that exists because we've taken resources that could have been available to the future generations. So by us consuming today, there is an opportunity cost, the cost of another alternative, the net benefits of another alternative that are considered a cost for all alternative. Remember, so the opportunity cost of any decision is the net benefit of the alternatives that are available. And so in this case, if there are two alternatives, we can consume today or we can consume tomorrow. Essentially what this means is if I choose to consume today, then the cost of me consuming today is the net benefits that would have occurred if people consumed in the tomorrow. Okay? And so essentially what this means is marginal user cost, which captures that net benefit, that opportunity cost, increases as we consume more today. And as we consume more tomorrow, then after tomorrow, the opportunity cost of after tomorrow will become the cost of tomorrow. and right, and it keeps on increasing and increasing and increasing, because as we consume more and more and more of a finite supply, then the opportunity cost continues to increase, and therefore the marginal user cost increases. That is the most important thing. You need to understand that, because when we're going to go into these graphs, you need to understand what I'm talking about. Okay, that's very important. So let's take a look at this. So when extending the time horizon, the only changes in this example from the 2-period case involve spreading the allocation over a larger number of years. And so we are extending the 2-period model into in this case, a 10-year timeline. Okay, and so as you can see, the first chart over here illustrates the quantity extracted and consumed. And so here we start off in year. This is year 1, we consume 8, and year 2 we go down and go down and go down, and by year 9 we're consuming 0. Okay, and now in the first case we are assuming a constant marginal extraction cost. So we talked about this, right? Essentially that means that if I'm going down that ore body, it's gonna have the consistent marginal cost, even if I go 20 kilometers below. Right? So it's always going to be constant. And so we have a constant marginal cost in the second graph and the increasing marginal user cost. So once again, so as we are consuming more in the present, so our consumption is higher here than it is here, then because we're consuming here, the opportunity cost, the net benefits that are foregone here are considered a cost here. Okay, and so therefore our opportunity cost continues to increase over time as we consume more and more and more, and eventually, they hit the $8 level. So we have a constant marginal extraction cost, an increasing marginal user cost, and falling quantities consumed over time, because there is a finite supply. We can't consume 8 at the constant level all the way through. Okay, now remember, total marginal cost refers to the sum of marginal extraction and marginal user cost. So TMC over here, this line over here, is the sum of the marginal extraction cost plus the marginal user cost, which is essentially the difference between these two. And so if marginal extraction cost is constant, then the difference is increasing, therefore the marginal user cost is increasing. So TMC is the marginal extraction cost plus the marginal user cost, okay? Now, total marginal cost is increasing. The increasing marginal user cost reflects increasing scarcity and the accompanying rise in the opportunity cost of current consumption. So as we consume more, the opportunity cost increases because the present value of net benefits in the future continues to increase. Now, the extracted quantity falls over time until it reaches 0. Okay? The consumption reaches 0, so at year 9 it reaches 0, where a total marginal cost is $8. In this example, the price of this good is assumed to be $8. So in the book, they give a more fuller example, and I don't really want to go into it, but essentially, they've presented this resource, this is depletable resource, which costs $8. Okay? And so consumption of a depletable resource under these assumptions falls to 0 when the total marginal cost curve reaches $8 and it equals the price. So when TMC equals the price, then consumption turns into 0, because it doesn't make sense. It's not profitable to consume that depletable resource anymore, because it would cost us more to consume from a total marginal cost perspective. Okay? Now, suppose for our previous example, there was a perfect substitute that is infinitely available at a cost of $6. So the price of the depletable resources is $6. Is $8, but the perfect substitute, the renewable resource, is $6. Well, as the total marginal cost curve increases, the transition to the renewable resource would occur because the $6 marginal cost is less than the max willingness to pay at $8. The total marginal cost for the depletable resource in the presence of a $6 perfect substitute would never exceed $6, because society could always use the renewable resource instead whenever it was cheaper. So let's take a look at an example. So it's the same as before, where our consumption is declining over time, once again, because it is a finite resource. So this is the consumption and extraction of a depletable resource. But once we hit the time period of $6, where the marginal cost of TMC equals 6, so once our TMC equalizes with the price of the renewable resource, then we make that switch. We make that transition to the renewable resource. Okay? So while the max willingness to pay, the choke price, which in this case would be 8, sets the upper limit on total marginal cost when no substitute is available, the marginal cost of extraction of the substitute sets the upper limit when available. So the upper limit of total marginal cost when there is no substitute and it is only the depletable resource is the total marginal cost of that depletable resource, which in that case was $8 before. Now, if there is a substitute, well, then the upper limit is essentially the TMC of that renewable resource, which in this case is $6. It's the price, right? So in this case, once it hits the total marginal cost in period 6, we switch to a consumption of a renewable resource. And it's the same thing here. So our marginal extraction cost remains constant as of right now, and our total, our user marginal cost, the difference between the two, increases because, again, we're consuming a depletable resource. But once we make that switch to a renewable resource, the total marginal cost remains constant because, again, it is a renewable resource. Okay? Because the renewable resource is available, more of the depletable resource would be extracted in the earlier periods than was in the previous example. And so this is quite important as well. So the consumption of our depletable resource is much more aggressive early on because we know that we can transition to a renewable resource once our total marginal cost reaches that respective level of $6. So we consume more knowing that we have a substitute for our depletable resource. And the switch point is where consumption of the renewable resource begins. And it is essentially right here. That is the switch point. So I'll be referring to that transition point as the switch point. Okay? Now, a close examination of the total marginal cost curve for each of the two resources reveals two characteristics. The first one is the transition is a smooth one. The total marginal cost curve never jumps to the higher level. And two, the slope of the total marginal cost curve is flatter after the time of the transition, so after the switch point. And so let's look at that. Let's take a look at the total marginal cost curves, right? So our the marginal extraction cost and the total marginal cost for resource 1 is the depletable resource, and resource 2 is the renewable resource. And so you can see that the extraction cost, the marginal extraction cost, is significantly lower for the depletable resource than it is for the renewable resource. However, you can see that the total marginal cost curve is significantly steeper for the depletable resource. And we talked about this. This is, again, because the opportunity cost that is foregone, the net present value that is gone from consuming today rather than tomorrow increases significantly as we consume more and more of that depletable resource. Whereas for the renewable resource, that opportunity cost is significantly less. In the end, because there's so much of that renewable resource available, then the opportunity cost that is foregone when we consume today rather than tomorrow is significantly less. And therefore, there is a smaller difference. And so the slope of the total marginal cost curve for the renewable resource is much flatter than this. The transition, so we talk about the first observation is that the transition, the switch point, occurs when the total marginal cost of the depletable resource equals the total marginal cost of the renewable resource. That's when it occurs. And 2, the second observation, the slope of the total marginal cost curve is flatter simply because the component that is growing, the marginal user cost, represents a smaller portion of the total marginal cost for the renewable resource. So as we talked about that already. Okay? Now, a more realistic assumption is to consider marginal extraction cost as an increasing factor. So realistically, I will be also starting up another video series on, mining and, taking a look at the mining costs and how to value mines. And so I was already started to read that textbook, and it's clear to me that as you go deeper and deeper and deeper into an ore body, the marginal extraction cost increases significantly. And so probably majority of the time you even see a huge capital cost because you transition from an open cut mine where it's really on the surface and you just dig down to an underground mine where you have to dig shafts to go all the way down a kilometer and then access the ore body. So there are increasing capital costs as you go more and more deeper, as you extract more and more and more. So relative to the previous case, the big difference lies in the behavior of the marginal user cost. Before, we assumed that marginal user cost increased by R, right? So when marginal extraction cost was constant, the marginal user cost increased by R. Again, the opportunity cost that was foregone in the future because we consume today. When the extraction cost increases, when the marginal cost of extraction increases, the marginal user cost declines over time. So that same cost now declines. Now, wait, what do you mean? We're still consuming now, and there are still going to be opportunity costs that are foregone in the future. Why? Why is the marginal user cost declining? Well, marginal user cost is an opportunity cost reflecting foregone future marginal net benefits. We already know that, okay? In this case, every unit extracted now raises the cost of future extraction, which diminishes the net benefit received in the future. So when we're talking about the present value net benefit in the future, the opportunity cost, we're not talking about just the benefits that are received. We're talking about the net benefits. So it's also accounting for costs. What this means is that if costs in the future are increasing, so if we're consuming right now in the present and the cost of extraction is lower in the present than it will be in the future, then that gap, that difference between the two will be significantly smaller. Therefore, the opportunity cost that is foregone by consuming today rather than tomorrow is much smaller, and therefore the marginal user cost declines. Okay? At the switch point, the opportunity cost of current extraction drops to zero, and total marginal cost equals the marginal extraction cost. Okay, so let's take a look here. So once again, we have this example. So the extraction and consumption of a depletable resource, we're consuming. All of a sudden, we make the switch point, okay? And we make the switch point at 7 years. So let's look at our TMC chart over here. So at 7 years, there's a switch point. And we have our marginal cost of extraction. So before, this was constant. This was moving like here. But because it's increasing, as it's increasing, you will see that the user cost, the marginal user cost, becomes smaller and smaller and smaller and smaller. Therefore, marginal user cost is declining, and you'll see that total marginal cost eventually gets to that point where it equalizes with the total marginal cost of the renewable resource, and then you make that switch. But this is so important. I think I'm going to go back one more slide just to talk about it again, because you won't get this if you don't, the difference, okay? So the key difference between this example and the previous example was simply that we changed the assumption that the marginal cost of extraction is now increasing rather than constant. Now, marginal user cost is an opportunity cost reflecting foregone future marginal net benefits, okay? So it is the net benefit that the future generation would have received if we saved consumption today and they were to consume the same amount of resources tomorrow. Now, if we extract some today, then the price of extraction increases. Therefore, the net benefit, the difference between the benefits earned and the costs of extraction in the future will be much smaller. And so, therefore, the opportunity cost will be significantly smaller than before, and therefore, our margin, as we increase and increase and the cost of extraction increases and increases, that difference, the difference between benefits and costs in the future, becomes smaller and smaller and smaller and smaller, which eventually illustrates this difference here, which the difference between the two, which is the marginal user cost, becomes smaller, 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 smaller until the switch point. Okay, and here this is the same as before. We're depleting, we're consuming less and less and less of the depletable resource up until we make the switch to a renewable resource, and then we're constant. Okay, so that's relatively simple. Now let's talk about exploration and technological process. The search for new resources is expensive. As easily discovered resources are exhausted, searches are initiated in less rewarding environments, such as the bottom of the ocean or locations deep within the earth. This suggests the marginal cost of exploration, which is the marginal cost of finding additional units of the resource, should be expected to rise over time, such as the marginal cost of extraction. So if you were to conduct and build a more advanced model, in addition to including the marginal cost of extraction, which would be increasing now that we're being more realistic, another more realistic assumption is to add the marginal cost of exploration. We won't do this in this video, but it is another important consideration that you need to know about. Some of this exploration would be successful. New sources would be discovered. If the marginal extraction cost of the newly discovered resources is low enough, these discoveries could lower or delay the increase in marginal cost of production. This would cause a slower decline in consumption, while the rise in total marginal cost would be dampened. So again, talking about how I want to start up this new course in mining and valuing mines, one of the big assumptions and one of the big considerations is the exploration budget of that mine. Majority of the time, you will see that the success rate of exploration is incredibly low. Why would a company spend billions and billions of dollars every year to dig holes in the ground and then just leave it there? Because it's just not profitable. Well, this is the point. The point is that we want to explore, and if we're lucky enough, and if it's a 5 or 6% chance that we can find that ore body that will lower our total marginal cost, then we can. It slows down the decline in consumption, while the rise in total marginal cost would be dampened as well. So it's really important from a societal perspective that those mining companies continue to explore, because in the grand scheme of things, although they will profit themselves individually by finding a new mine and then developing that mine, in addition, from a societal perspective and a dynamic resource allocation perspective, it's good for exploration. We need that exploration. It's not considered waste. Okay? Now, is it realistic to assume that a market with millions of self-interested parties would pursue such dynamically efficient allocations? So we were just talking about the purpose of mining companies and how they would spend billions and billions of dollars on exploration, and majority of it is wasted. Is that efficient? Well, yes, it is. In the end, many people see businesses as myopic, with the aim to extract and sell resources as fast as possible. That is not true. If the property rights structure is efficient and the three pillars of exclusivity, enforceability, and transferability exist, this is not true. Okay? When bearing the marginal user cost, the producer, the owner of that land, acts in an efficient manner. A resource in the ground has two potential sources of value: a use value when extracted and sold, and an asset value when it remains in the ground. So you will see when I value mining companies on Seeking Alpha, one of the components of my valuation comes from the exploration interest, because a company might own 2 or 3 mines and they might be mining the ore body, but at the same time they might own interests in these pieces of land, and they've already conducted some research and they say that, oh, it's really potential and we need to continue to conduct exploration and see if we should really invest in this. And so you'll see that valuation for the entire company not only comes from the use value, the sales and profits from the mine, but also the asset value that comes from the ground, the ownership of those exploration interests. As long as prices increase, a producer who sells all resources in the earlier periods loses the change to take advantage of higher prices in the future. Okay? So essentially what this means is that if you're truly assuming, as we go back here, many people see businesses as myopic, like they're very short-sighted. They would extract as much now and they wouldn't focus on the future. Well, if they were to really do that, then they'd be missing out on a big chunk of value. In the end, if they are consistent and they consistently increase the production quality, they can consistently increase the amount of ore milled while also holding different exploration interests, then you will see that they'll be maximizing their valuation. So it's not in their interest to produce and extract everything at the moment. It's in their interest to balance the two out, because in the end there are two different types of sources of value for that respective company. Okay? From an environmental perspective, the environmental costs that are not internalized by producers is one of the biggest failing of property rights structures. If environmental damage is not part of the extraction decision, two problems arise. And we've already talked about this in earlier chapters, talking about the social marginal cost curve and the private marginal cost curve. And essentially, the social marginal cost curve is higher, which therefore the price of the depletable resource is too low when we're only considering the private marginal cost curve. So we need to increase the price, and the extraction of the depletable resource is too high. In the end, quantity consumed and produced is too high when we're working solely off the private marginal cost curve. If we're working off the social marginal cost curve, then our quantity is consumed and extracted is much less. So let's take a look at the chart over here. So the dotted lines is the environmental. So if we internalize those environmental externalities, and the bold line over here is solely if we were to consider the private marginal cost curve, if we were not to internalize this. And as you can see, if we do consider environmental costs, then the consumption, the amount consumed and extracted is significantly less. And from a marginal perspective, a marginal cost perspective, total marginal cost is higher, whereas extraction costs are also higher, because we need to account for the environmental costs that come from digging up and damaging a forest or damaging a piece of land in order to take what's underground. right? If including environmental costs increases the total marginal cost curve, it increases prices and dampens demand. And this is also quite important. If environmental costs were associated with the depletable resource, the switch occurs earlier. Okay? Wait, what do you mean it occurs earlier? If we're consuming less, if we include the environmental costs, shouldn't this switch occur later? Well, no, because remember, our depletable resource is the switch point occurs when our total marginal cost equals the price of the renewable resource. Because the total marginal cost is significantly higher with environmental costs, independent of the amount consumed, in the end, the switch will occur earlier. And you can see right here just the intersection point. So the switch would occur in period 6 if we include environmental costs, and it would occur in period 7 if we did not. So it would occur earlier. On the other hand, if we were to be considering a constant marginal extraction cost, that would not be considered. Essentially, the switch would occur at the same point. Okay? Other than that, yeah, that's pretty much it for chapter 6. It was quite a chunky video. I think it went for quite a long time, but it is a very important one and a very realistic chapter. What frustrates me with a lot of economics courses that they're highly unrealistic and we make some assumptions. But again, like I'm studying a lot of mining courses right now, and what I see in this course and in specifically this chapter right now, you'll see a lot in a lot of other courses. So it's a very realistic chapter. So as always, I've provided the link to Tom Tiedenberg's 9th edition book in the video description, and also talking about the whole entire writing about different mining companies and oil companies. Check out my Seeking Alpha profile. Read up on some of my articles if you want. Please subscribe to my profile there. I'll be releasing a lot more articles and applying a lot of the concepts that I'll be talking about in this video series. Other than that, if you have any questions or concerns, comment in the video and I'll be sure to get back to you as soon as possible. Have a great day, guys.